Good evening, everyone. Thank you for being here. It's always a pleasure to speak to people in Bangalore because I know that at the end of the evening, there will always be great questions. So now there's a challenge to you, right? You have to be thinking about what questions you're going to ask after this. So I'm going to be talking to you about the future of contagion, and what I will say is that I built my academic reputation on a virus which I'm not going to talk about at all. And in my communications on public health, I have done a lot of talking about other viruses, and I'm going to try and ignore them as much as possible. So we'll stay with concepts as much as we can. And I've divided the talk into three parts: where we started from in terms of thinking about contagion, where we are now, and where we are going. So if we think about where we started from, this is a site in northern China called Hamin Manga. And this was discovered a few decades ago. It's a collection of really small houses that had been abandoned about 5,000 years ago. What's interesting about these houses is that not all of them are occupied. But in some of the houses, what you see, one of the houses in particular has 97 skeletons in it, or parts of skeletons. It's believed that what had happened in this community was an outbreak of some unknown disease, that bodies were kept in these particular houses, and then the houses were burnt over the dead bodies. So this is a site that has been discovered. Because of the burning, it's very difficult to recover from the bones what pathogens might potentially have caused this outbreak to happen. But within our recorded history, we actually have a lot of literature about contagion and the spread of infectious diseases around the world. Hamin Manga was an outbreak. The outbreak was contained by keeping the dead bodies in one place. But if we think about other things that have happened, I think the two diseases that people know the most about that have been recorded in history are plague and possibly smallpox. Small segues into tuberculosis, but because tuberculosis resembles many other things, we are never clear about whether it really was that illness or not. Now, if we think about what happened with plague, if you can see the colors in the map, the legend on the top gives you which year plague was seen in Europe. And if you look at the dotted line that is there, that is the line that was the border between the Mongols and the rest of Europe. So Russia and where the Mongols were, there was a barrier and people were not allowed to cross that area. But if you look at what happened, this area where the Mongols were was actually connected to Asia. And in 1346, you started to see disease there. And then if you follow the colors by year, you can see that the barrier held back the disease for about 3 or 4 years, but the disease actually came down and then spread upwards into northern Europe. Magnus VI, King of Sweden, thought that this was God punishing them for the misbehavior of the population, and actually did a public penance, which is quoted here. And you can imagine what it was like, that he could see what was happening in the areas that were west of his country, and you could see the disease traveling up into Sweden. Magnus actually ran from the plague and was able to move to Bergen and to other places ahead of the plague and survived that illness. But the plague killed up to 50% of the populations of many urban areas. So this was truly a pestilence that traveled all over the world. That pestilence was seen in the 14th century in Europe, and in India, up until the 20th century, we still had plague. Between 1896 and 1921, there were 12 million deaths. And this was the time when the British were here and had some ideas about public hygiene. So what they did was an ancient practice of quarantine, where you cordon off, or you have a cordon sanitaire, where you wall off the people that are infected so that they cannot spread disease outside. So they had special travel passes for people who could move across the borders of those cordons. And then when the outbreak was over, or enough people had died and the deaths had come down, what they used to do was disinfect the areas where the disease had been. Now, we know now that plague is carried by the rat flea, and there are different species of rats that can travel with people on ships, get around the world, and infect new populations. Interestingly for me, my family was in Punjab, and the claim to fame that my family has is that my great-grandfather actually received a commendation from the British because he was the local rat catcher. You used to cut off the tails of the rats and then submit them, and you got a reward for it. He apparently caught more rats than anybody in our village. So, infectious diseases control has a long history in my family. So if we think about smallpox, and that's another devastating disease, and is the reason why we have vaccines today. In the 1700s in Europe alone, about 400,000 people died every year of smallpox. Now, Benjamin Jesty was the person who first noticed that if you had a cowpox infection, that you would not develop smallpox. But Edward Jenner did the experiment that subsequently got reported to the Royal Society and then disseminated the idea of vaccination. And Edward Jenner's experiment was to take material from the lesion of on the skin of a milkmaid and then put it into what was then what would now be considered a very unethical experiment, because he actually inoculated the son of his gardener with that material from the cowpox lesion, waited 2 months, and then inoculated him deliberately with smallpox and showed that he did not develop disease. So James Phipps was the guinea pig for the first smallpox experiment that was widely described. And you can see him there. So smallpox was a devastating disease. There had been attempts in China and India to do variolation or insufflation with the materials from smallpox lesions. Those worked in some cases, but in some cases it was uncontrolled, and the people who were inoculated with material from people who had smallpox actually died of the disease. So cowpox was a safer way of getting a virus that was related to smallpox, where if you got vaccinated with it, you had pretty good protection from disease. So in 1796, you have the experiments. 1798, they are described. By 1800, vaccines were being administered across Europe and North America. So by 1900, smallpox had been eliminated from much of the industrialized world, and then it was eradicated from the Americas by 1950. When entire regions of the world became free of smallpox, the WHO had been established, became really ambitious, and said, we will try to eradicate this disease from the world. In 1959 was the beginning of the Global Smallpox Eradication Program, and in 1975 we had Rahima Banu, who was the last person infected with variola major. There was one infection of variola minor that happened in Somalia in Africa after that, but by 1979 WHO was able to declare smallpox eradicated. And so far, smallpox is the only human disease that has been eradicated. We've also been able to eradicate a measles-like infection in animals called rinderpest. So the reasons that we were able to do it to eradicate smallpox really had to do with vaccines and their role in prevention. So what are the features that led to eradication of smallpox? And this is really important when we think about diseases. Now, in smallpox, you saw the picture of the child. If you have smallpox and you can recognize it without a test, that becomes a very useful thing for public health. Would you care to compare smallpox and COVID? Did you know if anybody had COVID? Unless they had tested and told you that they were positive, you didn't know. The person looks normal. In smallpox, the person does not look normal. So if you see a person with smallpox, you can recognize the characteristic lesions of the virus. So it made it easy to detect cases without doing a test. The second thing that led to the eradication of smallpox was the lack of reservoirs. When a disease is limited only to humans, you know that a human has to be in contact with another human to be able to spread that infection. If you have no human contact, no spread of disease. Now, unfortunately, for many other infections, including SARS-CoV-2, this is an infection that can be spread to animals. So you may have heard about cats being particularly susceptible to COVID. Mink and white-tailed deer in the US got infected with SARS-CoV-2, and it was possible for that infection to then come back into humans. So whenever you have a reservoir, another species, where the virus can go and hide, it becomes very difficult to get rid of that virus from the community. The other thing was effective tools. Do you think for smallpox we vaccinated everybody in the world? Was our vaccine coverage so good that we made sure that everyone in the world was protected from the virus? Well, vaccine coverage today in children alone isn't 100%. So in the 1960s and 70s, clearly we were not vaccinating everybody in the world. But what we were doing was doing something that is called ring vaccination. And this is actually a strategy that was subsequently used for Ebola as well. So if you have a case which is at the center of the ring, you have one person who has the illness. What you do is get in there very quickly and vaccinate all the people that they have been in contact with. So if these people are vaccinated, they will be protected from the disease that this person has. And anyone that they come in contact with, they will be unable to transmit to. So this principle of ring vaccination of identifying a case early, getting in there with an effective tool, making sure that people around the infected person were protected, was what led ultimately to the eradication of smallpox. Right. So then the other thing that is really important to understand is, how do we understand whether a disease is actually related to an infectious agent? Now, when we had smallpox, there was no understanding of the differences between bacteria and viruses or parasites. Malaria, for example, is called malaria, bad air, because people thought that it was traveling in swamps that gave you malaria. They didn't realize that swamps were associated with mosquitoes, and it was the mosquitoes that were passing on a parasite that resulted in malaria. So the person that we have to thank, dressed in this rather fetching Japanese costume, is Robert Koch, who came up with what is known as Koch's postulates. And Koch's postulates essentially say, it seems absolutely incredible, but this is only 150 years of knowledge, that a particular disease can be associated with a particular pathogen, but to prove that, you have to use Koch's postulates. And that is that the same microorganisms are always present in every case of the disease. So you need to recognize the disease, you need to be able to identify the bacteria, viruses, parasites, fungi that are causing that disease. In Koch's postulates, the idea was you should be able to recover those agents, and then you should be able to reproduce that disease by giving those organisms into another healthy host. So usually, as in this picture, you could give it to mice. So this is an illustration from anthrax, which is a disease of sheep and cows, which can be transmitted to humans. But if every sheep that died of anthrax had these rod-shaped bacilli in them, those bacilli could be taken out, grown in culture in the lab, then given to mice, and the mice died, and you could get again from those mice the same organism again. That would be fulfilling Koch's postulates, establishing the relationship between an agent and a disease. Now, not only was it important for Koch to actually establish these postulates, he actually went around the world investigating disease. He and Louis Pasteur brought to them in Paris and in Germany lots of young scientists from different parts of the world that came there, studied the principles of microbiology, and then went back to where they came from and absolutely exploded our understanding of which diseases were caused by which pathogen. So Koch did a lot of identification of conditions. You know, Koch's disease is also tuberculosis. He identified the cause of anthrax, the cause of cholera. And what it allowed for people to do is to take our understanding of the pathogenesis of disease, the fact that bacteria or viruses produce damage in the body, and then tie them up with patterns of disease control. Now, this shown here is the pump, the water pump on Broad Street. And what we have in the gentleman in the coat is John Snow. John Snow was responsible for identifying the pump on Broad Street as the cause of cholera in London. What he did there was create a map of all the cases of cholera that were being described in London. He took his map and then looked to see what the water sources of all the houses with cholera were. He found that everybody was collecting, every household that had cholera was collecting their water from the Broad Street pump. and people in houses that did not have cholera had other sources of water. He removed the handle of the pump and the outbreak stopped. So John Snow is referred to as the father of epidemiology, and we still follow the principles that he laid down to be able to connect disease with what happens in populations and think about methods for control. We also had Louis Pasteur, whose very first vaccine was actually a vaccine for chickens. So first he saved the French wine industry by identifying the fungi that were leading to wine turning bad. And then he showed that the association that Koch had put forward could actually result in using the organisms that were identified as a cause of disease. You could do things to those organisms to make them protect against the disease that they caused. What he did was discover the principles of attenuation. He found that different microorganisms reacted differently. So for some, you could heat them either to a point of killing the organism or just repeatedly heating them to weaken them. Others you could expose to oxygen, and this was important for organisms that are microaerophilic or require carbon dioxide, and that results in attenuation. Still others you could treat with chemicals so that they would no longer cause disease, but when given to a host would result in protection. So he made the first live attenuated vaccine for animals for chicken cholera. Then we had other stalwarts of science, and this is all around the people who were responsible for building our understanding of infectious disease and the tools to solve them. So everybody's heard the story of Alexander Fleming and how he came back from a long time away, a longer than normal time away to his lab, and found that the Petri dishes that he had left out where a fungus was growing, the bacteria would not grow around that, and that was the discovery of penicillin. But before Alexander Fleming discovered penicillin, Paul Ehrlich, who had been working with dyes, had actually developed the first compound that was a specific treatment. He discovered salvarsan, which was a treatment for syphilis, which had been incurable up to that point. And I'd just like to point out that for all of these people who were working in labs at the time, the amount of effort that they undertook was humongous. Salvarsan was compound 606 that Paul Ehrlich evaluated against a model of disease. So you can think about the number of experiments that it takes for scientists to have one success story. So that's where we started from history, prehistory to the 20th century. And now to move on to where we are now. This is a map, a graph of life expectancy. And I've highlighted India here in 1901 and in 2001. Life expectancy in India was 23.5 years in 1901. In 2001, it was 63. Now we are at about 68. So pretty rapid progression. And much of this has to do with our ability to control infectious diseases. Why do we know this? I'll walk you through this figure, which is from the US. It's 96 years of infectious diseases in the US. You can see from the spike that the influenza pandemic from 1918 to 1920 was a significant cause of mortality due to infectious diseases. But as the US changed its approach to living conditions, a lot of infectious diseases declined before we had antibiotics and tools. So if you look at the period from 1900 to 1920, you had the establishment of health departments in states. You had people thinking about ventilation. You had the use of chlorine in municipal water. You had houses that were built better than the mud and adobe houses that they had previously. As you go through the 20th century, you begin to see what is happening with the control of vectors, understanding that if you have plague, then you need to be able to control the rats that bring plague into households. Only after 1940 do you start to see the effect of drugs and vaccines. So it's very important to understand that our living conditions and our behaviors play a major role in what happens with infectious diseases. Drugs and vaccines are a tool, but an understanding of infectious disease is the most powerful weapon that we have. So now I'd like to come to the differences between endemic disease, epidemic disease, and pandemic disease. An endemic disease is one that is with us all the time. So if I was to think about diseases in India, I'd say typhoid is an endemic disease in India, even though we might see small outbreaks of typhoid in some places. If you think about children, everybody knows that once your child goes to school, they acquire coughs and colds and fevers at a most amazing rate because they are being exposed to other people that are giving them infections. What are these infections caused by? The bulk of those infections are really respiratory viruses, adenoviruses, enteroviruses, if you have a fever with rash. Occasionally you have bacteria, strep throat and others that can spread between children. So these are endemic diseases. Epidemic diseases are the ones that cause small-scale outbreaks, sudden increase in cases. So if it's limited to a country or a region, it still is just an epidemic. What are examples of epidemics? Cholera, typhoid. Occasionally, you see some viruses causing disease. You could call Zika either an epidemic or a pandemic, depending on whether you can track its spread or not. When diseases cross continents, then they become pandemics. And examples we've had of recent pandemics include things like H1N1 and SARS-CoV-2. The number of outbreaks, epidemics, pandemics that we see has really increased over the last 30 years. And I like to use the alphabet, which starts with AIDS and goes to Zika, as an example. Obviously, there are many more than 26 causes of outbreaks that we have seen in the last 30 years. And the reasons for that are obvious to everyone. Increasing trade, travel, people living closer together, lots of migration, either because of conflict or because of climate change, changes in animal-human interactions because of deforestation, all kinds of reasons why things are happening. But this, I thought, might bring it home to you. These are travel routes in 1933 and in 2020. How long do you think it's going to take for an infectious disease to spread? So when we shut down the skies, we actually did limit spread of disease for a while. But when you have a disease that spreads asymptomatically, staying shut down forever isn't really feasible. Now, this is about looking at population density. So if you look at the number of people per square kilometer of land area, you can see that South Asia and some parts of Europe really are the densest populations in the world. So wherever you have people that are really close together, you are likely to get more spread of disease. And that's not really helped by the fact that we have a lot of rural-urban migration for, again, a variety of reasons. It's estimated that our urban populations will cross our rural population in the near future, and that just raises the risk of disease. Add to that climate change, you can see the areas where you're going to see more change happening in terms of global temperatures, and that's going to lead to a change in behavior of humans and the spread of animals and vectors. So if we think about outbreaks, most outbreaks that travel quite easily are caused by viruses. And if you take a look at the global risk report, you can see that the top risk by impact is really infectious diseases. And the top risk by likelihood, number 4, is infectious diseases. So if we think about the world, I think we no longer live in a world where we can afford to ignore the threat of an infection spreading across borders. So I'd like to just use one example to describe a recent outbreak. Now, this is Ebola in West Africa in 2014. 2015. Ebola had been described in human populations from the 1970s. Most often when Ebola occurred, it was a village in Africa that was in a forest somewhere, and it was easy to contain Ebola by walling off the village, by allowing nobody to move into or out of the village, and making sure that whoever was going to die in that village died in the village and the disease shut down there. When Ebola came into urban areas in 3 countries in West Africa, the cases just exploded. There had never been an Ebola outbreak with more than 1,000 cases before. This was close to about 30,000 cases with really high case fatality rates. But if you think about how we controlled Ebola, we actually went back to age-old methods of making sure that we had really good protection of people who were looking after Ebola patients. We know that Ebola was spreading because of burial practices, where people came in contact with the body of the person who had died. And as soon as you were able to restrict that, you could control the spread of Ebola. The problem was changing behavior and culture is really hard. How do you communicate to people the risk of Ebola? Now, people tried very hard to do this. They were successful in some situations. They had to use force in other situations. Patients who came into Ebola treatment units were out of contact with their families. The psychological damage, the emotional damage that was done to people is something that we don't really count. So if there was a way of preventing Ebola or protecting people from Ebola, that would be fantastic. But Ebola was an orphan disease. Ebola was not a disease that traveled across continents until it did. And then suddenly we kicked in and said, okay, we need to have a vaccine for Ebola. And you can see when the vaccine trials started, they really started when the outbreak was already waning. That was a problem and was actually the reason that a group of people came together and set up something called the Coalition for Epidemic Preparedness Innovations to make sure that if there were diseases of outbreak potential, then those diseases could have vaccines kept in reserve before the outbreak happened. Now that's logical, makes a lot of sense, but very difficult to execute. Nonetheless, it got set up, and that group then actually started to work on a number of vaccines. But there have been many outbreaks that we have handled really without vaccines or with vaccines appearing very late in the course of the disease. And this brings me back again to the point that I made earlier, which is that we can control diseases if we understand the disease epidemiology and pathogenesis. Vaccines allow us to prevent it, but even when a disease starts to happen, we do have tools that allow us to address both transmission and modulation of the severity of the disease. Nonetheless, for Ebola, we now have a success story because Ebola outbreaks can actually be cut off quickly with vaccinations. Since 2014 to 2024, we now have 2 licensed vaccines for Ebola that are widely available. Ebola cases keep cropping up, but none of them have reached the 28,000, 30,000 caseload that was seen in the West African outbreak. Coming now to where we are going. Now, vaccines and antibiotics have been our tools to prevent and treat infectious diseases, and we use them building on a base of a safer environment, better hygiene, better nutrition that allow us to handle infectious disease better. But our world is changing quite rapidly. So shown here is air travel across the world and in different regions. Here is export of goods that cross borders. And here is the urban population. If we are doing anything, we are setting ourselves up for outbreaks. We're doing well with controlling endemic disease. If we look at what's happening in terms of the burden of diseases that we have lived with for a really long time, diarrhea and lower respiratory infections in the dark pink coming down, NTDs and malaria. NTDs have come down significantly. Malaria came down, is going up again now because of vectors becoming resistant. HIV and AIDS, you can see that bump where it really took off, but we now have it a little bit more under control. TB declining, but very, very slowly. But overall, the picture for endemic infectious disease is looking good. But if you look at outbreaks, we have a lot of outbreaks that have been happening over the past several years. And we call them emerging if they are brand new, and re-emerging if it is a pathogen that we know that goes away for a while and then comes back again. So in this kind of environment, not only do we have risks from travel, trade, etc., we also have new risks. The level of air pollution that we see increases disease susceptibility. We tend to see, because our built environments are much more enclosed now than they were before, we tend to see much more persistent outbreaks of respiratory illnesses. And the behavior of pathogens that are transmitted through vectors is also changing as vectors change their range. So chikungunya in Italy, who would have thought? Okay, so if we look at vector-borne diseases across the world, the map on this side shows you what is where the vector-borne diseases really are. And you can see that it is a belt that is on either side of the tropics. And unfortunately, these are the areas where we are going to see significant changes in temperature over the next decades. And that's going to mean that we need to track these diseases much, much more carefully. And one of the problems with vector-borne diseases is that they can be quite difficult to treat. And if they develop resistance against the drugs that we have today, that's going to wind up being a problem. Now, another problem that we have in India is the idea of epidemiological transition. I'm talking to you about infectious diseases. But if you were to talk to the government about its priorities, if I was to talk to people in this room about their families and your priorities, I'm betting infectious disease is not what you're worried about. You're worried about diabetes, you're worried about hypertension, you're worried about the person who has cancer, right? That's epidemiological transition for you. So if you take a look at the map of India, what you see in the bright reds, you can see those are the places where communicable diseases are more important. If you take a look at the figure that is more in the blues, the darker the blue, the more you're worried about non-communicable diseases. Does this make sense to you? Well, I think when you think about India as a whole, this is what development also looks like. Along with development comes non-communicable diseases unless we are really, really careful. And the problem with having these diseases is that actually it changes the picture of infectious disease. So diabetes in India, we have a problem here because we are a country where the urban population, in some parts of the country, almost a quarter of people living in urban areas that are adults above a certain age are diabetic, or they have undiagnosed diabetes. And as soon as you have a non-communicable disease in an environment that is potentially contaminated, you actually get new concerns for infectious diseases. So everybody's probably heard about how diabetics have to take good care of their feet, and those are infections that come to them from the environment. But the other thing you have to think about is that there are specific infections that are more common in diabetics. So for example, malignant otitis externa, your external ear getting infected, usually with a bacterium called Pseudomonas. This is something that is 90% of this is seen in people with diabetes. You have an emphysematous pyelonephritis, which is not only a kidney infection, but a kidney infection that produces so much gas that you can see it on a plain X-ray. So the arrows there pointing out what is gas in the kidney. You have periodontitis, and all of this is because diabetes, as much as it is an endocrine disease, it also damages your immune system. So if you remember with COVID, we saw lots of interactions between people who had non-communicable diseases, much more severe when you get sick. And the same is true for tuberculosis as well. The other problem that we have is that we become trigger happy when we have tools to use, and overuse of antibiotics is leading to a situation where many of the diseases that we were previously able to treat, we are unable to do so now. So bacteria replicate very rapidly If they are constantly exposed to low levels of antibiotics, they can make mutations that allow them to become resistant to those particular antibiotics. So the more often you use antibiotics, the greater the chances that you are carrying on you antibiotics resistant bacteria, which if they cause an infection in you, will be something that is untreatable. This is a particular problem in India for tuberculosis, but also for people that get admitted to hospital. The antibiotics that we are using in our hospital are kind of our last resort antibiotics, and once they're gone, there's going to be very little available. So I really like this quote, antibiotics are like fire extinguishers. We are happy to have them on the wall, but we shouldn't be using them all the time. So if we think about the future of contagion, what do we know? We know that infectious diseases will continue to be a threat, endemic diseases, emerging diseases, re-emerging diseases, disease X, which is the mystery disease that will come from we don't know where and cause we don't know what kind of disease, and we have to worry about bioterrorism. Infectious diseases, especially those that transmit from people who have no symptoms, can spread very rapidly around the globe. Some of the tools that we have are under threat. If we have a combination of non-communicable diseases and communicable diseases, that actually lowers our ability to be able to handle that disease. But science has brought us to a place where we can make tools very quickly that may be useful. There's lots of stuff we don't know. Where's our next outbreak coming from? What will cause it? How big will it be? Most importantly, will countries actually cooperate with each other and share the resources that we have? Despite best intentions, not much of that happened last time around. But given all of these changes, I think there is a recognition now that we do need to think about infectious disease in a much more nuanced way so that we can handle problems when they arise. The science that gives us the tools must be supported. This is a beautiful illustration of how we've done with discovering new antibiotics. As you can see here, the last class of new antibiotics that we got came to us in the 1990s after discovery before that. And we are now in a situation where we have very few new classes of antibiotics that are looking promising. This is despite the fact that the Hindu science section will always tell you that there is a new antibiotic that's going to solve all the problems in the world. That's usually in one mouse in the lab somewhere. Similarly, I think it's important to point out that we thought COVID-19 vaccines were made very quickly, but it was actually 40 years of research that led to our ability to make COVID vaccines in 1 year. Without that foundation of thinking about viruses, thinking about vaccine technologies, we wouldn't have had any of this. So if we think about what's next, the Moderna vaccine was designed in 2 days, produced in 6 weeks, and introduced in 9 months. What should preparedness look like for drugs, for vaccines, for diagnostics, for thinking about what we will need to do with population behaviors or with policy? What's next? You know, we've had Nipah outbreaks in Kerala for a really long time, and we don't have an answer. If you have a disease that appears out of nowhere, what do you do to prevent it? Can you really stop fruit bats being around humans? Can you stop humans eating fruit? Can you stop people being in contact with each other? Can you stop, how is every hospital prepared to handle Nipah patients when a Nipah patient appears once a year in one place and then there's nothing for 2 or 3 years. How do you maintain expertise in the clinic, in the lab, to be able to do this? So it is a challenge. Data, of course, is critical. How much do we need? Where should it come from? How is it used? All of these are really important. And I think we have very real opportunities here because of the way the world is becoming more and more digital. The nice thing about digital data is you can actually get signals. So we used to want pure, clean, nice, curated data. But I've found that with a lot of people that are dealing with big data now, dirty data is okay, because if there is enough of it, you'll still be able to get signals from it that have utility. So collection of data, as many sources as possible, and use of data, as many types of data as possible, in order to build a picture of what is really going on. So a changing world requires changing science. We need new data sources. One of them is to be able to do serosurveys, to be able to do genomic surveillance. And I'd like to particularly call out some work that was done in Bangalore by the Tata Institute for Genetics and Society and collaborators across Bangalore and outside, that was really around environmental surveillance. You'll be amazed what you can learn about pathogen by sampling sewage and wastewater. It gives you a signature of what is going on in communities upstream. So thinking about new data sources and how we use them for outbreaks of disease is something that is an area that we really should be considering and deepening our expertise in. So to end, there's really not been ever a more exciting time to be a scientist, whether it is genetics or it is AI or it is infectious disease modeling in animals and humans, populations around the world. There is so much opportunity for us to think about what we can really do to be prepared for pandemics, epidemics, smaller scale outbreaks, and use those learnings also for endemic disease. So with that, I'd like to thank you for your attention and move to the next item on our agenda, I think.
Yeah, thank you so much. Thank you for, providing this long arc of the infectious diseases and how our responses have evolved over time. A couple of slides towards the end really caught my attention, which talks about the known and the known of the unknown. I mean, what we know, we don't know, right? I'm just wondering, is that how big is this unknown to be causing some kind of worry? Or we think that what science and its tools has given us all this while should give us enough confidence to be able to, if not tame the unknown, but at least, handle it.
So I'll start by saying I have great faith in science and in human ingenuity, because so far we haven't had an outbreak that has managed to kill all of us or significant proportions of all of us recently, right? So I think we got really lucky with COVID, because for the bulk of people, I know it sounds crazy to say we got lucky, but if this was a virus that had a case fatality rate that was more similar to MERS, which is a cousin of SARS-CoV-2, then you'd have a third of people that got infected with it die. Instead of which, we know that case fatality rates are less than 1%. So that's why I think that, for a virus that was really transmissible, we were still able to handle it really well. Now, That said, what is your unknowns? I think we have the ability, and one of the things we are doing now is scenario planning. So, could you come up with a situation where you attribute certain characteristics to a pathogen and then model what it would look like to have an outbreak of that pathogen, whether it is something that travels through the gut, or it is traveling through the respiratory tract, or it's transmitted by contact, and it has these kinds of pathogenetic mechanisms. How do you build to control that? So, scenario planning is an exercise that public health agencies have begun to do, mostly right now as tabletop exercises, but in the UK, they actually get much more engagement of public health authorities to run these response plans. And the more of this kind of modeling we can do, the better prepared we will be.
So connected to that, I mean, I really liked when you said that changing times need changing science as well, because science cannot be static as well. What is your sense of, in that sense, the state in India in terms of how prepared we are in terms of this changing scientific research? Yeah.
So I think we have a lot of good people in India. We have good institutions in India. What we don't have is connections with each other. So we don't make up bodies of work. We don't make up associations that then influence both science funding as well as policy. If we were to come together and speak more with one voice, I think we could have more influence. Right now, we tend to be islands, and it depends on which committee you wind up on and how loudly you speak, whether you get accepted or thrown out of a committee.
Okay. I think you touched on it, but one of the constant tensions in the history of public health is about, how that one is about investing in, these drugs, whether antibiotics or vaccines or others, but also getting the basics right in the sense of, your living conditions, your immunity, sanitation, etc. Do you think that, that's important for infectious diseases, as we said, but do you think that we give enough emphasis to do that, or our focus is a lot more on getting, drugs or vaccines or whatever? Where are we in that sense of, or this is something is very difficult to do?
So, if you think about living conditions, again, on a long arc, things have changed in terms of how people live and what they do for behaviors. So, I'll give you an example of sanitation. So, I started to work in a tribal community around 2005 or so. In a population of 80,000 people, there were 6 toilets. And if you look at where they are now, there are some villages where 90% of households have toilets. Other villages have crept up to 20 or 30% of villages that are using toilets. So I find that if you say things should change tomorrow, that's not going to happen. But if you engage with communities over a long period of time, everybody seems to move towards living in conditions that provide for better hygiene, for better supply of water, for better sanitation. You start with a mud floor and then you go to brick or cement and then tile and above that. So if you take a look at houses that have been in villages over a long period of time, the number of houses that you find now that are mud and thatch is a very small proportion of where we had started. And that's to me, at least an indication that things are improving across our society. Maybe not as fast as we would like, but certainly as fast as people can afford to upgrade their living standards.
Perhaps this is the last question before I hand it over to others. Is that, see, one thing is to have science. Science tells us how to deal with whether it's HIV/AIDS or whatever. But that doesn't mean that it reaches everyone, right? You spoke about, in the sense of even, the immunization coverage for children. How do we ensure that science is able to, because there is no point in celebrating science otherwise, saying that, okay, we have cracked COVID-19, we have cracked, maybe something else will come tomorrow. What do you think that we need to keep in mind in terms of that science actually is for people and science reaches everyone? Yeah.
I think science, I think science is not about necessarily the tools that we produce, right? It's more about a way of thinking. It's about, do we trust in God, but everybody else, please bring evidence? So if we have the kind of mindset that says that I will make my decisions based on information that I have that is credible, to me that is scientific thinking, and that's something that should be inculcated in schools. Question things. Make sure that when you make a decision, it is actually informed by knowledge and not by opinion. And that's going to lead to a society that is capable of doing more for itself.
Right. You said this is the exciting time to be a scientist. So what is the one advice to maybe young scientists? Yeah.
So I think the one thing I would say for young scientists is learn as much as you possibly can about the techniques that are coming online. Sometimes it's really difficult to put yourself outside your comfort zone. I am an economist. I don't do molecular biology, or I am a molecular biologist, but I only work in proteomics and not in genomics. Well, stretch yourself, because it is in that stretching that you get insights that will make you better at whichever field you've chosen.
Very important. Okay. I know I can see many, many hands. So just request you to be precise in your question. So I'll go here. Yeah. Somebody's passing on the mic.
Yes. Yeah. Hi.
Okay.
So I wanted to ask about there is challenge in academia when it comes to reproducibility, right? And you also showed in your slide that a lot of antibiotics were discovered almost like clockwork until maybe last 20 years. Are these two kind of linked? Because you're saying that, okay, there is a vaccine that works maybe in one mouse, but you can't discover classes, or what is it? Are these two kind of linked?
So I think reproducibility and the ability to advance discovery are two different things. Reproducibility, if you take a look at an experiment in mice and an experiment in humans. In mice that are inbred, you can do an experiment in 6 mice and you will get really tight results. They will be very similar to each other, very small ranges. You take 6 humans and you do the same experiment there, your results will be all over the place. That's because humans are more heterogeneous. So if you wanted a reliable result in humans, you'd need a much, much larger number. So designing experiments so that you get results that are actually generalizable across the populations or the systems that you are studying requires you to design the experiment well, understanding what heterogeneity in that population looks like. Reproducibility comes from a range of different sources of error. It can be the person, it can be the temperature in the room, it can be, did I shake something for 15 minutes instead of 20 minutes? So those are things that should be controlled by having an SOP that you stick to, an operating procedure that you stick to really closely. But heterogeneity leading to results that you cannot generalize across populations is the important part of discovery that you must pay attention to. Thank you.
Good evening, Dr. Kang. This is a full fangirl moment for me because I'm an immunologist. So it's thrilling to hear you speak live. I have a two-part question about vaccines. The first is we've had an outbreak. I don't know if it's an epidemiological outbreak, but definitely by empirical evidence, an outbreak in the city of dengue. I think it still continues if you talk to doctors here. I remember reading somewhere about a Swiss vaccine in development, and I wanted to ask you where we are in that in the world, and if India has plans of procuring it, if you know of it. And the second is what I find very curious about this whole anti-vaccine movement that you notice about, that you read about in the United States, you hear young mothers talk about it in India, and I have to sort of hold myself back from going full passionate, like, what's wrong with you people? But I'm curious on your thoughts on both. Thanks.
Okay. So for dengue vaccines, there are two licensed vaccines, one made by Sanofi and the other made by Takeda. There is a third vaccine that is being manufactured in Brazil that's going to be available shortly. The Sanofi vaccine is not licensed in India. The Takeda vaccine, I think, is close to licensure if it isn't already licensed. But the important thing to remember about dengue vaccines is that you need to do serology first before you give the vaccine, because you want to give it only to people who have had prior dengue exposure so that they don't develop severe dengue when their antibodies decline. The vaccine that's being made in Brazil says that it won't have those problems. It will be a single-dose vaccine. Don't know yet. So that's the dengue story. The vaccine hesitancy, vaccine lack of confidence story. Well, there's one way to think about it. There is an entire spectrum of the population. There are people that really believe in vaccines, people who will take vaccines if they are told to take vaccines, people who are a little bit hesitant, but you can convert into takers by talking to them. And then you have the rabid ones that will not be convinced no matter what you do. So the important part is figuring out where on the spectrum people lie and whether it is worthwhile for you to invest any time if they are never going to change their minds.
Hi, my question is regarding the pandemic preparedness. So as you know, there is a WHO pandemic preparedness agreement or a pandemic treaty that's currently in talks. And in fact, it was one of the priorities. Stuck. It is stuck, yeah. So it's difficult to get the member states to agree on everything. So do you think it would dramatically improve the pandemic preparedness globally and not just for high-income countries? If yes, how?
So one of the problems that I have, and these are complex political discussions that are happening, but if I was to look from an Indian perspective at the global situation, for rich countries, it is really about what's our best situation for protecting ourselves, right? It's not truly about the good of the world. I'm being a bit skeptical here, but I think it is justified skepticism. Then they turn around and point fingers at countries like India saying, you didn't share data, you didn't share vaccines, Indonesia for sharing their strains, and India for sharing vaccines. But they never question their own decisions. So every country has a certain level of self-interest. And I think that is going to be the barrier to the pandemic treaty. There are bureaucrats and diplomats in the room. I think they're the ones that know what negotiations need to be undertaken to get it across the finish line. I don't think I have an answer to that.
Good evening, ma'am. So just one question. What role do you think the disease surveillance using the technology like machine learning tools have a role to take care of the future contagion?
So machine learning relies on data, right? So who generates that data and what form is that data in? If there was a way of just a clinical picture giving you an idea of what the disease is, then it might be feasible. But at the moment, we're still at a stage where you need to marry the clinical data with testing for a pathogen. So both disease and the cause of disease before you say you have something that can be input into a data system. Once you have that, then you can think about machine learning being predictive of what might happen in the future. If I see this signal today, this is what is going to happen 2 weeks or 1 month from now.
Good evening, ma'am.
Sorry. Yeah. Hi.
Hi. So I think you talked about vaccine cycle time being brought down to a year or even less, right? And so new vaccines are being found. But actually on bacterial infections, that antimicrobial resistance seems to be a fairly serious threat, especially in India where we use it extensively. OTC, we collect it from, from the, so I was really shocked. 87 was the last molecule, right? That was from your slide.
Yeah.
So what cycle time will it take and why is it being ignored in some way, right?
So this actually raises the interesting question of which antibiotic has the greatest value and the greatest effect. It's the antibiotic that is used the least. So which company is going to invest in R&D for an antibiotic that people are going to say should sit on a shelf and only be used in a small set of circumstances? So there is a lot of thinking around this process. Should you have a prize? You develop a new antibiotic, but we'll give you $5 million to never use it. What price is right? Especially now when you have drugs for gene therapies that are in the tens of millions of dollars. What is the right price for making a drug and then not using it? So most companies are out of the antibiotic discovery business because they find it very difficult to come up with a new molecule that's not going to have an extensive market.
Okay. This is a question from our Bhopal campus, and this is from one of the students in Master of Public Health. I think you partly answered to one of his questions, but this is about AI and how AI is going to help in health systems response in terms of infectious diseases. And as a public health student, what is the scope of work in future on this?
So in terms of AI, there is a lot of involvement of AI in antigen discovery, in drug discovery. What it allows you to do is not to come up with the final product, but actually to eliminate the stuff that you don't need to waste time on. So it narrows your pipeline very efficiently. And that's something that we will probably see more of going forward. I'm sure there are going to be other applications of AI as well, but these are the ones that are most advanced at the moment. In terms of students of public health, well, I think everyone that has an interest in public health will contribute in some shape or form to the control of disease. I mean, if you think about public health, and I had this conversation at the university earlier today, The best thing that we can do as public health practitioners is to keep people away from healthcare. What does it take for us to promote health so that people don't need to come to see a practitioner?
Yeah.
Okay.
Yes.
Sorry. Yeah.
Sorry, can I?
Okay. Yeah.
Okay. Yeah.
Please go ahead.
Okay.
Go ahead, because
Yeah.
we'll give them the mic. Yeah.
Sorry. Yeah, I just had the whole COVID phase actually brought up, sort of brought together different countries in very different ways. Some of them obviously being, extremely research driven, who obviously contributed to the vaccine development, and then India sort of being the vaccine factory of the world. You must have seen at close hand different countries and their strategies. In some sense, COVID was sort of a leveler, right? A lot of countries, even though they were Western countries, more advanced, also had, suffered a fair bit across both America and Europe. And then India, surprisingly, I mean, we would have thought it might have fared a lot worse, but eventually probably did pretty well on the, in the grand scheme of things. What exactly did we probably do well, and what did we not? And why did some of the Western countries also struggle? What exactly was this?
We did many things well. I think number one was make lots of vaccine and make it very quickly. We had enterprising companies that engaged in that, very early on. By May, Serum Institute was having discussions with many organizations outside the country about what they could bring in, and finally it was the vaccine from the University of Oxford. Similarly, many other companies were doing the same thing. What we did really well to have lower levels of damage due to COVID is we had a younger population. So the countries that saw really severe disease all have populations that skew older. Any countries, so Africa and Asia, all saw lower mortality rates. Even if you say it was, more than it was reported to be, we still had lower mortality, and that was because our population is younger. Only 10% of our population is over 60.
Yeah, Madam, my question is, there have been a lot of reports in the newspaper, this vaccine for Covaxin or Covishield is causing a lot of side effects on the people.
Yeah.
What is your opinion on that?
All vaccines have side effects, but the side effects tend to be rare. So whenever you have a vaccine, the vaccine is given to healthy people to prevent disease. So if a vaccine has a lot of side effects, that vaccine is not going to progress. All of the vaccines that we had for COVID were tested in 25,000, 30,000, 40,000 people. So if there was risk, that risk was 1 in 10,000, 1 in 20,000, 1 in 40,000 people, right? Whereas if you look at the benefit side, the attack rate of COVID was so high that the vaccine was creating a lot of reduction in severity of disease in a much larger number. So for every side effect, you actually have much greater benefit. And depending on which vaccine it is, that benefit-risk ratio varies. But absolutely, vaccines do have side effects. They're just very, very rare because no vaccine is licensed without testing it in thousands of people.
Hello. I wanted to ask, do countries really share data? And maybe you could shed some light on this vis-a-vis COVID 4 years on. Do you have access to, forget the public, but all of you, medical practitioners, scientists, have easy access to all the data that you need to get on with your work?
So I think in terms of COVID, a lot of official country data sharing with WHO went on. So WHO was publishing situation reports weekly at the beginning of the pandemic, and that was a really useful source of data. Many countries wound up putting dashboards on their websites. Many states in India had really good dashboards. For example, Kerala's dashboard was one that I would go to very frequently because it gave you a really accurate picture of what was happening in that state. So some states made their dashboards openly available. Other states kept their dashboard for their officials. But people were operating on the basis of the data they had. And I think the ones that did the best were the ones that had the best data to be able to structure their responses. It's not easy to get people to share data across borders within countries and across countries.
Thank you. I know that this is something that we could just go on and on, but unfortunately we have to stop here because he has to catch a flight. But thank you everyone, and thanks a lot, right? We learned a lot. Yeah.
Once again, on behalf of the BIC, I'd like to thank Dr. Kang and Professor Mishra for the session. Thanks to all of you for your questions, and thanks to the entire Azim Premji University team. As previously mentioned, some of their publications are outside. Do take a look and stay updated on our forthcoming events on the BIC website. Thank you, everyone. Have a good night.